So Roman numeral number 1 on unit 2.2 talks about the period and the frequency. The period is the time for one cycle, and the frequency is the number of cycles per second. With units of hertz, that is actually cycles per second. Okay, so what this means, if you want to look at an equation or how we'll use it if we're using numbers, it means that the frequency is 1 over the period. And conversely, the same thing, just flipped upside down, that the period is 1 over the frequency. Okay, so depending on which one you're given, that will determine which one you use. Okay, this is an inverse relationship. If one goes up, the other goes down. So usually I'll just write an arrow for goes up. That's what we mean by an inverse relationship. Okay, so what does that mean for frequencies? Okay, that means that higher frequencies accomplish more cycles per second, and thus they have shorter periods. Okay, one way to write that is if F goes up, then T, the period T, goes down. Okay, and also for lower frequencies, we'll have longer periods. Meaning if the frequency goes down, the period goes up. That's what the inverse relationship means. So question number 2 says, does a 300 hertz tone or a 900 hertz tone have a longer period? Okay, so from these statements here, the lower frequency has the longer period. If F goes down, then T goes up. So that means for 300, the answer is A. So 300 hertz has longer T or larger T than 900 hertz. Okay, so you can remember that one just from the relationship. Okay. Number 3 is actually asking you to find the period. Okay, so it says, what is the period? So T is our question mark of a 500 hertz tone. So F is equal to 500 hertz. Okay, so then you can come up here and you say, I'm looking for T and I'm given F. So I'm going to use that version there. T equals 1 over F. I put in the 500 here. That's again cycles per second. So that would be, if you do 1 divided by 500 on your calculator, then you would get 0.002 seconds. And that is equal to 2 milliseconds. That little m is standing for milli because that would be moving the decimal place 3 points to the right. Okay, so that is D, the answer for that one. All right, so that's the relationship between the frequency and the period. Okay, so now moving on to masses and springs. The natural frequency F for a mass spring system okay, we're never going to use this equation. I'm just writing it out so you can look at it. We're just going to use the relationship that the stiffness is on the top and the mass is on the bottom. Okay. What does this mean? Because the stiffness is on the top, that means that the frequency F and the stiffness have a direct relationship. What does that mean? A direct relationship. If one goes up, the other goes up. Okay, and then frequency and mass Ooh, stiffy. Have an indirect relationship. Okay, that means that if one goes up, increases, then the other goes down. Okay, that's our general relationship for how the stiffness and the mass impact the frequency of the oscillation, the natural frequency of mass spring systems. We're going to use this relationship throughout our class to get approximations for other more complicated systems. Okay. All right. So question number 4 says, if the mass doubles, the spring stays the same, what's going to happen? The frequency is going to increase because mass, is it going to increase? No. Mass doubling means if the mass increases, mass and frequency have an inverse relationship. So that means if the mass increases, the frequency decreases. Okay, so that would be B. Number 5 says, consider 2 springs, one is stiffer than the other. The same mass is used, which one will have a longer period of oscillation? Okay, so it's going to be a 2-stepper. First, we're going to figure out what the frequency is going to do, and then we'll figure out what the period is going to do. Okay. All right, so stiffness of the spring. If stiffness is larger, then the frequency is larger. They're directly related. But then if we look back up to our inverse relationship with the frequency and the period, that larger or higher frequency is going to correspond to the period being shorter. It's a direct relationship there, inverse relationship there. Okay, same idea, but if the stiffness is smaller, so a less stiff string, then the frequency is smaller or lower, because they are directly related, but the period is inversely related to the frequency, as we see up here, 1 over the frequency. So the smaller or lower frequency will have a longer period. Okay, so and when I say stiffness is smaller, that means a looser spring. And when I say stiffness is larger, that means the stiffer spring. Just trying to get all these words connected here for us. So the answer is that the longer period will come from the looser spring. All right, so on the back, Roman numeral number 3 now, we have a picture with the potential energy, which I'll abbreviate PE, of the pendulum. This is gravitational potential energy, and it is proportional to the mass, the gravitational constant, and the height h. Okay, and so the potential energy of the pendulum is greatest for the same mass when h is largest. What is h? H equals the distance above the lowest point, or reference point. Okay, so PE is greatest at A and E in the picture. Kinetic energy is associated with the motion. We won't ever put numbers in the equation, but just if you want to see it, is directly related to the mass and related to the square of the velocity. Okay, so that kinetic energy, okay, is greatest when the speed is the largest. So v is equal to the speed. It's a v because it could also be velocity. Okay, so that means that where is this pendulum moving the fastest? It's moving the fastest at C, the bottom of the arc. This is the pendulum. Okay. Now, if we think of the displacement, so displacement is equal to the distance from equilibrium from the resting position okay, and then it will be a plus if it's above or to the right of the resting position, and if it will be a negative if it's below or to the left of the resting equilibrium position. Okay, so it's the distance plus the sign. Okay, so when we have this displacement versus time graph, okay, displacement t time a or t, pretend it's a sine wave. Okay, this upward would be everything positive would correspond with a compressed spring, and everything negative would correspond to an extended spring. All right, and so let's think about kinetic energy. Okay, so we have our spring. Okay. And let's say this is the equilibrium position here with some mass m. And this is, let's say, the compressed and then extended. And then that's the extended version. Okay. So this point, all of these peaks here, I'm going to label it as A, would correspond to the most compressed spring. These points, these marks with the X's, correspond to going through equilibrium position. Okay, so these are all at A. And then these points that I'm marking B are when it is fully compressed, extended spring. Okay. So at A and B, the extremes, okay, what happens there is that the mass stops for a hot sec, as my 18-year-old would say. That means that V equals 0. That means that the kinetic energy at those points is 0. Okay, and it also means the potential energy is a maximum because that is the maximum displacement. And the potential energy for a spring is 1/2 k, which is the spring constant times x squared. Again, we will never use that equation. That's just there if it helps you. Okay, so the larger, so PE and x squared are have a direct relationship. So if x is greater, if x squared is greater, then PE is greater. Increases. So the maximum x squared will correspond to the maximum PE. The squared means it doesn't matter if x is positive or negative. So let's give a little example of that. If f equals +3, x squared equals 9. If x equals -3, x squared also equals 9. Okay, so that's why the potential energy does not depend on whether the displacement is positive or negative, will have the same quantity of potential energy. Okay, so at the extremes, at A and B, that's what the situation is. Okay, at X, which is notated here by our equilibrium position. Okay, it's when the displacement equals 0, when this curve crosses this line. Okay, this is when the mass is moving its fastest. Okay, in other words, the speed is max value. And it passes through the equilibrium position. Such that the potential energy equals 0 because X equals 0. Little x. Okay. I'm going to put C's on all these big X's just so we can try to keep it straight. So C or little x equals the distance from equilibrium. Or displacement if it has the plus or minus sign. Okay, hopefully that is helpful. Okay, and then number 4 is the idea of resonance. So just really quickly, I will give a definition, but there are many more in the slides. Okay. Resonance occurs when something is driven at its natural frequency. Another way to say it is that the driving frequency, the frequency of whatever is doing the pushing, supplying energy, is equal to the natural frequency. That's the definition. And then the result in very large amplitudes vibration. Hopefully that helps. Bye.